In the previous session we have seen what are languages. Now in this session let us take few examples of finite automata. So after these examples I think the finite automata will be clear to you. Okay. So let us say we have the language L1 which is saying set of all strings starting with the symbol A over the alphabet summation is equal to A comma B. Assume this is the language. Okay. Now in this language what are the strings here? Strings will be A, AA, AB, ABA, AAA and so on. That means the initial alphabet should be A. It does not matter what is the alphabet or what is the string which you are getting after this initial single A. Okay. So initially you should get an A. Fine. Now for this we have to draw a finite automata. So if you want to draw a finite automata, first of all you should know what are the basic symbols or what are the basic elements of a finite automata. Okay. So in this diagram we are going to use something called as state. A state will be drawn something like this. We will be using something called as final state. A final state will look something like this. We will be using something called as initial state. The initial state will look something like this. And then we will be using something called as transition, which will look something like this. Okay. So these are the basic elements of this finite automata diagram. Okay. Now you should know what is the basic structure of a finite automata. So in this finite automata what we use is there is a tape like this. This is called as a tape, right? There will be something called as read-write head. So this is read-write head. This is the tape. Then we will be using something called as finite control, and we are also going to have a finite memory. So we will be having a finite memory, and this finite control can read or write something onto this memory. Fine. Now you should know why we are drawing this finite automata. A finite automata is basically representing your computer machine. All these machines which you are going to study in this subject, they all are called as abstract machines. Finite automata is an abstract drawing or abstract diagram of a computer, and every language here is going to represent a program which you are going to load into that machine. So in this subject we want to identify what are the limitations and powers of your computer system as a machine. Fine. So here what we do is, in this tape we'll be having some alphabets, for example A, B, and so on. Okay. So this tape is something like, if you have seen the old cassette players maybe you will be having some old music players or cars, then you must have seen something called as cassette players, and all these cassette players we had something called as a tape. So this is a similar tape, which it can be a magnetic tape or it can be a physical tape. Fine. So from this tape, this finite control is going to read a symbol. It is going to read a symbol, and after reading the symbol, this head will move into this direction, right? And after reading the symbol, this finite control is going to transition from one state to the another state. Now after reading this complete string, if the finite control is at the final state, right? In all the states, if the finite control is at the final state, that means the string is accepted. Okay. So what do I mean to say here is, don't worry if it is not clear to you, just see what the finite automata is. If we say this is a finite automata, okay. Now to this finite automata, if we give a string of the language, for example in this case the string can be single A, the string can be ABA, the string can be AAA or any other string. To this finite automata, if we give a string of this language, then this finite automata is going to make transitions according to the symbols in the string, and after reading the complete string, the finite automata can be at the final state. So if the finite automata is at the final state, that means the string is accepted, or if the finite automata is not at the final state, that means the string is rejected. That means the string is not present in that language. Okay, so let me repeat it again. We will be having a finite automata. For one language, we are going to draw one finite automata. To that finite automata, if we give any string to this finite automata, then this finite automata will make transitions by reading the symbols of the string. After reading the symbols of the string and making a transition, and if we read the complete string, that means if we from here to here, if we read the complete string, and after that complete string we are going to get something called as epsilon symbol, then after reading the complete string, if the finite automata is at the final state, that means the string is accepted. But if the finite automata is not at the final state, that means the string is rejected. Okay, so what do I mean to say accept and reject? Accept means that string which we gave to the finite automata is present in this language. Reject means the string which you gave to this finite automata is not present in this language. Okay, now let us see a basic diagram here. Here we are saying it is the set of all strings which are starting from the alphabet A. Okay, now let us see how a finite automata looks like for this. We have something called as an initial state. This is the initial state. Okay, so let us name the state as A. Now if we read a single symbol A, then we will go to a state B. In the state B, we are here because our string is started from the symbol A. Now after that we can have any number of A's or any number of B's, but initially if we got a B, then we are going to go to state C. After this we can have any number of A's or any number of B's. Okay, now what is this diagram? Okay, let us see what I have done here. Let us suppose we are giving the string A, B, A to this finite automata. Okay, so that means on the input tape we have loaded the string A, B, A, and after that we will be having an epsilon symbol. Fine. So this finite control is initially reading the symbol A. Okay, for this language we want to check whether this string is present in this language or not. So initially the finite control is reading the symbol A. So when in the initial state we are at this state A. After reading the symbol A, from state A we will go to the state B. Okay, now we are reading the second symbol. In state B, after reading the B, we are again going to the state B. Okay, then we will read the third symbol. We are at the state B. After reading the symbol A, we are again at the state B. Now we have completely read the string. Now after reading the complete string, if we are at the final state, that means the string is accepted. It means that this string is present in this language. Now after reading this complete string, yes, we are at the state B, therefore this complete string is accepted here. Okay, now let me take one more example. Let us say we have some string which is not present in this language. Okay, now let us say we have the string which is B, A. Let us suppose we want to see if this string is present in this language or not. Okay, so initially what we are going to do is, initially the finite control is reading the string B. So we are at state A. On state A, initially if we read the string B, then we will go to the state C. Yes, we are at state C and we are reading the symbol A, then again we will go to the state C. Yes, we are at state C If we read the symbol A, then again we will go to the state C. Yes. Now after reading the complete string, if we are at the final state, that means the string is accepted. But if we are not at the final state, that means the string is rejected, right? So after reading the complete string, we are at the state C, and the state C is not a final state. State C is not a final state. Hence, this string is not present in this language. Okay? Now, see, it is not necessary that for any language we may be having a unique finite automata. We may be having more than one diagrams of a finite automata for any given language. Okay. Now let us take few more examples of finite automata before giving a final definition or formal definition of this finite automata. Fine? Okay. Now let us take one more example here. Let us say we are working on the symbols summation is equal to a comma b. These are the symbols. Okay. And let us say we have the language which is set of all even length strings. Set of all even length strings. Okay. So what can be the strings which are present here? Strings can be phi, not phi, it will be epsilon here. The initial string can be epsilon, because phi means an empty string and epsilon means a string of length 0. Why I am saying string of length 0? Because string of length 0 is an even length string. Okay. Now we can have strings of length 2. What are the strings of length 2? They are AA, AB, BA, BB. We can have strings of length 4. So what are the strings of length 4? There will be AAAA, AAAB, AABA, AABB, ABAA, and so on. We can have strings of length 6, we can have strings of length 8, we can have strings of length 2n, right? So here all these strings are of length or are of even length. Fine. Now let us suppose if we give a string to a finite automata and we draw a finite automata for this specific language, and we want to identify whether the string is present in the language or not. Okay. Now what I am saying is, let us say we give the string A, B, A, A, B. Assume we are giving this string to the finite automata. Okay. So what will happen here in case of finite automata? We will load this complete string onto a tape. So we are loading the string onto a tape. Okay. We have a finite automata. Let us draw the abstract diagram of a finite automata. We have a state A. Fine. Then after reading a symbol A, we are going to state B. Right. Here the length of the string is 0. That means string length 0 should be accepted. Now after reading the symbol A or by reading the symbol B, we are at state B, and here the length of the string is 1, that means the odd length. Now after reading the symbol A from B or reading the symbol B from B, we are at state C, which is also a final state because here the length of the string is 2. Now after reading the symbol A or reading the symbol B, we are at state D. Here the length of the string is 1. Now after reading the symbol A or reading the symbol B, we can go to some state and so on. So this diagram can continue. Right? Now this diagram can continue. Why this diagram will continue? Because the language, the number of strings in the language is infinite. There can be infinite number of strings in the language, and here we cannot have infinite number of states because it will be practically impossible for you to draw infinite number of states. Now the question is, can you minimize this finite automata? Right? Can you have minimum number of states here? Now let us say how can we have minimum number of states here? We can have something like this. We can have a state A initially, which is representing strings of length 1. We can have a state B, which is representing strings of length 2. We can have a state C, which is representing strings of length 3. Then again we can have strings of length 4. This is 0, 1, 2, 3, 4, 5, 6 and so on. Right? Can we have a smaller diagram as compared to this? Let us try if we can have a smaller diagram here. Let us say we have initial state A. After reading the symbol A, I am going to state B. Fine. From B, I can again come to state A and so on. Okay. So this is how we can represent this same diagram into a minimum diagram, where whatever the pattern which we have here, what is the pattern here? Here this complete pattern is repeating every time. This pair here is, here is this pair, here again we have this pair, again we will be having this pair, again we will be having this pair. So whatever the pattern we have, we are repeating that pattern into a loop. Okay, so don't worry if you don't understand this, just follow with me. After the end of the complete session, you will understand what I am saying practically. Okay, so what I am saying is, now let us suppose if you want to see whether this string is present into this language or not. Okay, don't worry if you cannot draw this. So we will be having more than 20 or 30 examples here. After all these examples, you can easily draw any finite automata. Right? So assume we have this string and we want to know whether this string is present in this language or not. Now if you want to know whether this string is present in this language or not, we will give this string to this finite automata. This finite automata is present in this language. Now if after reading the complete string we are at the final state, that means the string is accepted. Okay, so let us say initially we are reading the symbol A. Now we are reading the symbol A. Okay, so let me just introduce one more thing here. We are at state A. We are reading the symbol A. After reading the symbol A, we are making a transition, that means from A we are going to state B. This is called as a delta function, which is the transition function. That means it is saying that if we are at any state, if we read a symbol, then after reading the symbol, to what state we are making a transition, or to which state we are going, right? So from the state A, after reading the symbol A, we are going to go to the state B. Fine. Now we are reading the second symbol. Now we are at state B here. Now if we are at state B, if we read a symbol B, that means if we are at state B, if we read the symbol B, then from B I am going to the state A. Therefore we are making a transition to state A. Okay, now let us read the next symbol. Now we are having the symbol A. So after reading the symbol A, we are presently at state A. So we will make a transition to the state B. That means we are at state A. After reading the symbol A, we will make a transition to state B. Now we are reading the symbol small a again. We are at state B presently. Now if we read a symbol small a, we are at state B presently. If we read a symbol small a, then we will make a transition to state A. Therefore we will again go to state A. Okay. Now we are at state A and we are reading the symbol B. That means we are at state A and we are reading the symbol B. We are at state A, we are reading the symbol B, then we will go to the state B. Okay. And now this state B, after going to the state B, we read the complete string. After reading the complete string, so whatever the state which we are at which we are, now if this state is a final state, that means the string is accepted. But you can see B is not a final state. Because B is not a final state, that means the string is not accepted and this string is not present in this language. Right? Now if I say the string is accepted, that means the string is present in the language. If I say the string is not accepted, that means the string is not present in the language. Okay? So that means after reading this, by reading the string is not accepted or it is rejected. Fine. So now I think you have an idea what I am saying here. Now let me give you a formal definition of finite automata. Okay, and then after giving this formal definition, we will take more examples here. Okay. Now what is a finite automata? So finite automata can be defined as, it is Q summation Q naught delta and f. It is a quintuple. A finite automata is a quintuple where q is denoting the set of states, summation is denoting set of input alphabets, q naught is denoting the initial state, delta is denoting the transition function, and f is denoting set of final states. Okay, here q is a non-empty set of states. Here I can say it is a non-empty set of states. That means at least we should have one state. Summation is non-empty set of input alphabet. We can have at least one input alphabet. We have exactly one initial state. We cannot have more than one initial states. Delta is a transition function, and this transition function is defined as q cross summation takes us to q states. Now we'll see what is this. And f is the final state, set of final state, and this can be an empty set. Here we can have an empty set. Okay, so what do I mean to say from this? Okay, now let us explore it with a small diagram. In the previous example, we have seen a finite automata for a language where the length of the strings will be even. Okay, so that means for even length strings we had this finite automata, right? We have already done this. Fine. Now for this finite automata, let us just give this formal definition. So we have this finite automata FA is Q. Q means set of states. So what are states here? States are A and B. That means the states which we have is A and B. This is a set of states. Summation is set of input alphabets. What are the set of input alphabets here? They are A and B, small a and small b. So we have small a and small b as the set of input alphabets. Then Q naught is initial state. So what is the initial state here is? Initial state is A. So this is the initial state. Then we have delta as a transition function which we will define now. So assume I'm just writing here delta. And then we have F which is set of final state, and what is the final state here? Only A is a final state. Therefore we have A as final state. So this is the definition of this finite automata where we have to define what is delta. Okay, and delta is a transition function. So what this transition function is going to say? It is going to say if we are at state A, we see a symbol A, then we will go to the state B. Now if we are at state A, we see a symbol B, then we will go to the state B, right? If we are at state B, we see a symbol A, then we will go to the state A. If we are at state B, we see a symbol B, then we will go to the state A. So this transition function is going to define if we are at a particular state, we see a symbol, then to what state we are going to. Okay, and this is the definition of a deterministic finite automata. So more precisely I should write this, it is a definition of a deterministic finite automata. There is a very small difference between the definition of a deterministic and non-deterministic finite automata, and that difference is given by this transition function only. Okay, so initially I am just going to define what is the transition function for DFA. There is a very small difference here. Okay, so let me define what this transition function delta is. Delta is, we say, you have seen this, how the delta is defined. Delta is defined in such a way, see, it means to say if we have a set Q which is the set of states, that means we have A and B as the set of state. If we take a cross product with summation, which is a set of input alphabets, what are the set of input alphabet here? They are A and B, small a and small b, and then we will go to the state Q. Okay, so then we will go to the state Q. Not state Q, actually the set of states. Okay, what does it mean? It means to say, if we are at Q, if we are at this A, if we see a symbol A, then I can go to a set of states. Okay, that means it is denoting a relation here. It is denoting a relationship. So as you already know, every relationship is a subset of a cross product. Okay, if you don't know this thing, then we are going to see this thing in discrete mathematics. So right now, for now, just assume that every relationship, but not relationship, I'm saying, I'm going to say, if you have a relation, every relation is a subset of a cross product of two sets. Okay, fine. So if we are at state A, we see a symbol A, then we'll go to state B. If we are at state A, we see a symbol B, then we'll go to the state B. If we are at B, we see a symbol A, we'll go to state A. If we are at B, if we see a symbol B, then we'll go to state A. So for this diagram, this thing applies. Okay. Now this cross product says we can have any combinations of these things, right? Any combination of AA, AB, BA, BB, or any other combination, right? So this is how a finite automata is defined. I hope it is clear to you. Now let me take few more examples of finite automata and let us go through this complete session. Right? Now let us draw finite automata for the following languages. Let us say we are working on the summation is equal to A comma B. Fine. So first finite automata is let us say language is set of all strings of length less than equal to 2. We can have languages set of all strings of length exactly 2. We can have languages set of all strings of length greater than 2. Okay, or I can make it greater than equal to, but let us say it is greater than okay, let us make it greater than equal to 2. So these are three languages, and for these three languages we want to draw finite automata. Okay. Now what is the first language? Set of all strings of length less than equal to 2. So what are the strings which will be present in this language? Strings will be epsilon, we can have single A, we can have single B, we can have AA, AB, BA, BB, only this thing. We can see why, because this is length 0, length 0 is less than equal to 2, this is length 1, length 1 is less than equal to 2, this is length 2, length 2 is less than equal to 2. Okay. Now what are the strings which will be present in this case? Strings will be AA, AB, BA, BB. And what are the strings which will be present in this case? Strings will be AA, AB, BA, BB, AAA, AAB, ABA, and so on. Fine. Now for the first language, let us say we have to accept epsilon, strings of length 0, we have to accept strings of length 1, we have to accept strings of length 2. Okay. So let us draw a finite automata here. Strings of length 0, that means initial state is a final state, then only we can accept strings of length 0. Okay. If we have single A or we have single B, then we can go to state B, which is also a final state. Okay. If we get single A or single B, then we will go to state C, which is also a final state. Right. So this is representing strings of, this state is representing strings of length 0, this state is representing strings of length 1, this state is representing strings of length 2, but we should not accept any string whose length is greater than 2. Okay. Therefore, if we get single A or single B, then we will go to state D, which is a trap state in this case. and then we have A and B n number of times, will be at the state only. Okay, so we'll take examples here, don't worry. So next is set of all strings of length equal to 2, right? So length exactly equal to 2, we have already seen this diagram, fine. So what is this? If we are at state A, strings of length 0, this means strings of length 1, this means strings of length 2, exactly 2, right? And this means strings of length more than 2, we should not accept anything after this, fine. Now next is set of all strings of length greater than equal to 2, fine. So this is the state A, strings of length 1, strings of length 2, right, and we should accept every strings whose length is greater than equal to 2. Okay, now we have these three finite automatas. Take a look at this first one. If you do not understand what I have done here, see, if we get epsilon, we are at state A, so we'll remain at state A, therefore the string will be accepted. Now let us suppose we have the string B, therefore if we are at state A, if we give a string B, then we will go to the state B. State B is a final state, therefore the string is accepted, right? Now if let us suppose we have string A, we want to give this string to this finite automata. That means after reading the first A, we make a transition from A to B. After reading the second A, we make a transition from B to C. After reading the third A, we make a transition from C to D. So after reading the complete state, are we at final state? No, we are not at final state, therefore the string is not accepted. Fine. Now if we say we have the string A. Again, if you read the complete string, then you are not at the final state, because this state D is acting as a trap state. So this is acting as a trap state. So what is a trap state? Trap state is a state that if you go to this state, then you will never be able to come out of this state. Okay, that means if you are at state A, then I can come out of the state A to B, I can go from state B to C, I can go from state C to D, but if you are at state D, then we will always be stuck at state D. We cannot go to any other state. So this is a trap state. I hope you can understand this diagram. So it is very simple here. Now if you see this diagram, here state D is acting as a trap state. So what this state D is, assume we have the string A. Fine. Again, if we have strings, okay, take a simple example first. Again, let us suppose we have a string of length 1. If we give the string of length 1 to A, then we'll go from state A to B, and B is not a final state, therefore this string is not accepted, right? So if we give a string B, that means if we are at state A and we'll take a string B, then we'll go to state B. Now if we give a string of length 2, then from the first symbol A will go from A to B, from the second symbol B will go from state B to C, and this B string, complete string will be accepted because C is a final state. Okay. Now if you give the string A. Now from first A will go from A to B, from second A will go from B to C, from third A will go from C to D, and D is not a final state, therefore the string is also not accepted. So this finite automata will accept strings of length exactly 2. Again same with this diagram, if we have string of length 0, then we will be at state A, which will not be accepted, string will not be accepted. We have string of length 1, that will be at state B, again string will not be accepted. Now if we have string of length 2, then we will be at state C and string will be accepted. If we again give a string of length 3, then we will be stuck at state C only, C is the final state. If we give any string whose length is greater than equal to 2, then we will always be at state C, and state C is the final state. Okay, again saying the trap state is, this is a state, if we go to this state, then we will never be able to come out of this state, and we will never be able to reach the final state. Okay. Now let us see these three diagrams. What do you understand from these diagrams? So if you see here, the string of length less than equal to 2, string of length exactly 2, string of length greater than equal to 2. Okay. Now if I say in general, if we have strings of length less than equal to n, So this is a string of length less than equal to 2. If we have string of length less than equal to n, then how many states will be required in such a DFA? Okay, now check this. For this DFA we have 1, 2, 3 and 4. That means 2 plus 2 is 4. Right? In the same way, if we have strings of length less than equal to n, in that case, in every case for deterministic finite automata, we are going to require n plus 2 states. Okay, how many states are there? 1, 2, 3, 4 in this case. If we have strings of length less than equal to 3, then we will be having 3 plus 2 as 5 states. Okay, now if I say the length of the string is only less than n but not greater than or but not equal to n. So here if I just remove this symbol, then how many states will be required? So we will see this again. Now if I have the string, the length of the string is less than 2 but not equal to 2. In that case, what will be the finite automata? Finite automata will look something like this. Initial state A. If we read a single A or B, then we will go to state B. If we read a single A or B, then we will go to state C, and this state B and state A will be final state, and after this nothing will be a final state. Okay, so here if the length is less than 2, the number of states are 3. If the length is less than equal to 2, then the number of states are 4, because here this state will also be final state, but this state will, both the states will merge in this case. That means in that case you will be having n plus 1 states. Okay, in the same way, if we have strings of length exactly n, in that case we are going to require n plus 2 states. Why? Strings of length 0, strings of length 1, strings of length 2. Again one trap state. Okay, if we have for n states, strings of length 0, strings of length 1, strings of length 2, strings of length 3 up to so on, strings of length n, there will be n states like this, and then one trap state. Okay, in that case we will be requiring n plus 2 states. Okay, now if I say strings of length greater than equal to n, see, greater than equal to n, then how many states are there? There are exactly 3 states. Right, so that means we will be having n plus 1 states. Fine. Now if I say strings of length only greater than n, then how many states will be required? So take it as only n plus 2 states. How these n plus 2 states are required in this case? So for this we have to draw A comma B, A comma B, A comma B. Fine. So roughly for this diagram you can say it is strings of length 0, strings of length 1, strings of length 2, and this is strings of length 3. Right. So any string of length 3 plus 1 or 3 or greater than 3 is accepted here. Again here, if we have strings of length greater than n, that means strings of length 0 to n, and then one extra state. So it will be having n plus 2 states. Right. So in general this formula is applicable. Right. Now let us take more examples here.